Welcome to the first outcome, where we get to grips with the energy that flows in and out of chemical reactions. We'll look at exothermic and endothermic changes, activation energy, the standard enthalpies, bond enthalpy calculations, calorimetry, and Hess's law. Every chemical reaction comes with an energy change between the system and its surroundings, and we measure that as an enthalpy change, given the symbol delta H. Over this outcome, you'll learn to read enthalpy profile diagrams and understand activation energy, define and use the standard enthalpy changes, and calculate delta H both from bond enthalpies and from experiments. We'll finish by applying Hess's law using enthalpy cycles. Let's fix a few terms first. Enthalpy, given the symbol H, is the heat energy stored in a chemical system at constant pressure, and the enthalpy change, delta H, is the heat transferred to or from the surroundings during a reaction, measured in kilojoules per mole. The system is just the reacting chemicals themselves, while the surroundings are everything else: the solvent, the container, and the air. And remember the key pairing. An exothermic reaction releases heat, so delta H is negative, while an endothermic one takes heat in, so delta H is positive. In an exothermic reaction, heat flows out of the system into the surroundings, so the temperature around it rises. The products end up with less enthalpy than the reactants, which means delta H is negative. Take the combustion of methane at minus 891 kilojoules per mole. You meet this every day in burning fuels, respiration, and neutralization, and it's exactly how a hand warmer works, using the exothermic oxidation of iron. An endothermic reaction is the mirror image. Here, the system takes heat in from the surroundings, so the temperature falls and things feel cold. The products store more enthalpy than the reactants, so delta H is positive, as in the thermal decomposition of calcium carbonate. Photosynthesis is endothermic, and so is dissolving ammonium nitrate, which is the trick behind an instant cold pack. So why do these energy changes happen at all? It comes down to bonds. Breaking a chemical bond always takes energy in, so it's endothermic, while making a bond always gives energy out, so it's exothermic. In any reaction, old bonds break and new ones form, and delta H is simply the overall balance between the two. If more energy is released, making bonds than was needed to break them, the reaction is exothermic. If it's the other way round, it's endothermic. An enthalpy profile diagram is a lovely way to picture this. Enthalpy runs up the vertical axis, and the progress of the reaction runs across the bottom. For an exothermic reaction, the reactants start high. The curve climbs to a peak and then drops to a lower level for the products. That peak is the transition state, the point of highest energy, and because the products sit lower than the reactants, delta H is measured downwards and comes out negative, with energy released to the surroundings. The endothermic profile flips that around. This time the reactants start low, the curve rises to its peak, and the products settle at a level above where we began. Because the products are higher than the reactants, delta H is measured upwards and is positive, with energy taken in overall. The shape tells the story. The products are storing more chemical energy than the reactants did. Whatever the reaction, there's an energy barrier to get over first, and that's the activation energy, written EA. It's the minimum energy the reactant particles need to start reacting, the gap from the reactants up to the peak of the curve. Particles have to collide with at least this much energy, so a high activation energy means a slow reaction at room temperature. A catalyst helps by offering a route with a lower barrier, and every reaction, exothermic or endothermic, has an activation energy. Let's put the two side by side. In an exothermic reaction, heat is released. The surroundings warm up. The products are lower in enthalpy than the reactants, and delta H is negative. Think combustion or neutralization. In an endothermic reaction, heat is absorbed. The surroundings cool. The products are higher in enthalpy, and delta H is positive, as in photosynthesis or thermal decomposition. Keep that contrast clear in your head. Let's pause and test yourself. If a reaction makes the water go cold, is it exothermic or endothermic? And what's the sign of delta H? Is breaking the bond in a hydrogen molecule endothermic or exothermic? And on an enthalpy profile, what does the peak of the curve actually represent? Have a think before we carry on. Because enthalpy changes shift with the conditions, chemists agree on a fixed set of standards, so everyone's comparing like with like. Standard pressure is 100 kilopascals, that's 1 bar, and the temperature is usually stated as 298 Kelvin, which is 25 degrees Celsius. Any solutions are at a concentration of 1 mole per cubic decimeter, and each substance is in its normal physical state under those conditions. We flag a standard value with a little plimsoll symbol on the delta H. Now, 3 important definitions, and notice they all start with 1 mole under standard conditions. The standard enthalpy of combustion is the change when 1 mole of a substance is burned completely in oxygen. The standard enthalpy of formation is the change when 1 mole of a compound forms from its elements in their standard states. And the standard enthalpy of reaction is the change for a reaction happening in exactly the molar amounts shown in its equation. The standard state itself is just the most stable physical form of a substance at 100 kilopascals and the stated temperature. Let's take combustion in more detail. Here, 1 mole of fuel is burned completely in plenty of oxygen, and for a hydrocarbon that gives carbon dioxide and water. For example, methane plus oxygen reacts to give carbon dioxide and water, and methane's standard enthalpy of combustion is minus 891 kilojoules per mole. Combustion values are always negative because burning always releases heat. And note that under standard conditions, the water comes out as a liquid. Formation is about building a compound from scratch. 1 mole of the compound forms from its elements, each in its standard state. So for methane, that's solid carbon plus hydrogen gas reacting to give methane, with a formation enthalpy of minus 75 kilojoules per mole. Here's a handy point. The formation enthalpy of any element in its standard state is 0. So oxygen gas and graphite both come in at 0. Formation values can be negative or positive, and they're widely tabulated for use in calculations. The standard enthalpy of reaction is the most general of the 3. It applies to any balanced equation using exactly the moles written and gives the overall change for that specific reaction. For instance, nitrogen plus hydrogen reacting to give ammonia has a reaction enthalpy of minus 92 kilojoules per mole. The value depends entirely on the equation and states you write, so if you double the equation, you double delta H. Combustion and formation are really just special cases of this. Time for another quick check. Can you write the equation whose enthalpy change is the standard enthalpy of formation of liquid water? Why is the standard enthalpy of formation of oxygen gas equal to 0? And what 2 products must form for a value to count as the standard enthalpy of combustion of a hydrocarbon? Give those a go. Let's turn to bond enthalpies. A bond enthalpy is the energy needed to break 1 mole of a particular bond, measured in the gas state and quoted in kilojoules per mole. Since breaking bonds takes energy in, these values are always positive. We use average values because the same bond behaves slightly differently from one molecule to the next. The carbon-hydrogen bond isn't quite identical in methane, ethane, and chloromethane. Some typical figures: carbon-hydrogen is 413, the oxygen double bond is 498, oxygen-hydrogen is 464, and the carbon-oxygen double bond is 805. Here's the rule for finding delta H from bond enthalpies. It's the sum of the bonds broken minus the sum of the bonds made. So you add up the enthalpies of every bond broken in the reactants, add up every bond made in the products, and subtract the second total from the first. A negative answer tells you the reaction is exothermic. Just make sure you're working from a balanced equation with the correct structures, so you count every bond. Let's work through the combustion of methane. We break 4 carbon-hydrogen bonds and 2 oxygen double bonds, so that's 4 times 413 plus 2 times 498, giving 1652 plus 996, which is 2648 kilojoules per mole going in. Then we make 2 carbon-oxygen double bonds and 4 oxygen-hydrogen bonds. That's 2 times 805 plus 4 times 464, giving 1610 plus 1856, or 3466 kilojoules per mole coming out. Delta H is bonds broken minus bonds made, 2648 minus 3466, which comes to minus 818 kilojoules per mole. The negative sign confirms it's exothermic. Now the hydrogenation of ethene, where ethene plus hydrogen gives ethane. Breaking bonds, we've got 1 carbon-carbon double bond, 4 carbon-hydrogen bonds, and 1 hydrogen-hydrogen bond, 612, plus 4 times 413, plus 436, which adds up to 2700 kilojoules per mole. Making bonds, we form 1 carbon-carbon single bond and 6 carbon-hydrogen bonds. 347 plus 6 times 413 comes to 2825. So delta H is 2700 minus 22825, which is minus 125 kilojoules per mole, a nicely exothermic addition reaction. It's worth being honest about the limits of this method. Bond enthalpies are averages taken across many different molecules, so the real bond in your particular molecule may differ from the average, which makes a calculated delta H approximate rather than exact. On top of that, bond enthalpies only apply to gases, so the method ignores any energy changes when substances are actually liquids or solids. That's why experimental values are usually more reliable than calculated ones. Calorimetry lets us measure that heat directly in the lab. The heat picked up by the water is given by Q equals mc delta T, where m is the mass of water in grams, C is its specific heat capacity of 4.18 joules per gram per degree, and delta T is the temperature rise of the water in degrees Celsius. You then work out the number of moles of fuel burned, and the enthalpy change is minus Q divided by that number of moles, converted into kilojoules per mole. Let's put that to work burning ethanol. We burn 0.23 grams of ethanol, which has a molar mass of 46, and it warms 100 grams of water by 20 degrees. First, the heat gained by the water, Q is 100 times 4.18 times 20, which is 8360 joules, or 8.36 kilojoules. Next, the moles of ethanol. 0.23 divided by 46 is 0.0050 moles. Then delta H is minus 8.36 divided by 0.0050, which gives minus 1672 kilojoules per mole. The data book value is minus 1367, so our experiment falls a fair way short, which leads us nicely to why. So why is the measured value out? Mostly it's heat loss, warmth escaping to the surroundings and the container rather than going into the water, which is why the ethanol result came out too negative. Incomplete combustion plays a part too, producing soot and releasing less heat, and some of the fuel simply evaporates without burning. The conditions aren't truly standard during the experiment either. A draft shield and a metal calorimeter help cut these errors down. Hess's law is one of the most useful ideas in this whole topic. It says, the total enthalpy change for a reaction is independent of the route taken, depending only on the starting and finishing states. That follows directly from the conservation of energy. Its real power is letting us find delta H values that are difficult or impossible to measure directly. By building an enthalpy cycle that links known changes to the one we want. The direct route always equals the sum of the indirect route. To use a cycle in practice, you draw the reactants and products and then find a path through data you already know. Follow the arrows carefully and remember that reversing an arrow reverses the sign of delta H. With formation data, the reaction enthalpy is the sum for the products minus the sum for the reactants. With combustion data, it's the other way round, reactants minus products. Keep a close eye on your signs and the number of moles, and always check the equation is balanced before you start. Let's try a cycle with formation data, finding the reaction enthalpy for the combustion of methane. The rule is products minus reactants. For the products, the formation enthalpy of carbon dioxide plus twice that of water is minus 394 plus 2 times minus 286, which comes to minus 966 kilojoules per mole. For the reactants, methane is minus 75 and oxygen is 0, so that's minus 75. Delta H is minus 966 minus 75. In other words, minus 966 plus 75, giving minus 891 kilojoules per mole, exactly matching the enthalpy of combustion of methane. Now a cycle using combustion data, this time to find the formation enthalpy of methane. With combustion data, the rule flips to reactants minus products. The reactants are carbon and hydrogen. Minus 394 plus 2 times minus 286 gives minus 966 kilojoules per mole. The only product is methane at minus 891. So delta H is minus 966 minus 891. That's minus 966 plus 891, which comes to minus 75 kilojoules per mole, the formation enthalpy of methane. One more check before we wrap up. Can you state Hess's law in your own words? For a reaction using formation data, what's the equation you'd use to find the reaction enthalpy? And in that ethanol calorimetry experiment, can you give 2 reasons why the measured value came out more negative than the true value? Have a go before you move on.